Howdy, students. We're going to talk about scalars and vectors, but mostly vectors today because it's super helpful to know how to use them, how to break them into components, how to use the resultant to break it into the parts. We're going to do all of that today and more. So, magnitude, I'm going to talk about it. It just means the size of something. And scalars are pretty much just magnitude. Temperature, distance, time. All we care about is the size of each of those things. But vectors are quantities with both magnitude and direction. So we're thinking displacement, velocity, acceleration, and in the next unit, forces. We've talked a little bit about one, gravity, but we'll talk about many more. And all of those are vectors because the direction matters. Sometimes you're going to see vectors represented, probably in upper level courses, as bold or arrows, or using both. Typically, I'm a little bit lazy about this, and as is College Board, that's why I don't think I've ever seen them take off for not representing vectors as bold. But in the future, they might. So I'm going to introduce it to you now. Force, like I said, is a vector. There's a box here. It's got an arrow that has a vector, and oftentimes vectors are shown as arrows, as we've been doing. As you can see it here, there is a 15-pound force on the box to the left. We can add them together. If we add vector A to B, we use the tip-to-tail method, as I've been talking about, and the resultant vector is the vector, or the sum of the two vectors, called the resultant. It's when you draw from the tail of one to the tip of the other. That is an added vector. Simple case, if you have no, if you are only going in one dimension, you have A plus B. The resultant is just going to be it added together. Those two things added together. This is a pretty good demonstration of that, except it's going to be demonstrating the two vectors going in the same dimension, so just flat, but one is going to be going to the left, and one is going to be going to the right, and I'll show you so you can see.
I have a feeling that we are very close to a perfect demonstration. We're going to see that ball drop.
With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check
Keep
the high
watch.
speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
They have the exact same velocity forward and the exact same velocity backwards, and as such, it falls exactly.
It's going straight down.
Vector addition! See how excited she is? Velocity was canceled out because the two vectors added, or in this case, subtracted.
I can't be happier. We actually got the speed of the car to match the speed of the soccer ball, and we got a perfect straight down drop.
Ladies and gentlemen, the laws of physics are still hard at work.
So true. We can add 3 together as well. We have A down and to the right, B down and to the left, and then C straight to the right. The resultant if we add A, then B, then C, the resultant's going to be right there. However, if we add B, then A, then C, completely different order. What? Exactly the same thing. If we had C, then A, then B, what? So it doesn't really matter. You're going to get the same resultant no matter what order you add vectors in. That's the coolest part. there's a lot of cool parts. Same direction, same size, doesn't matter the order. And that's really great if we're making diagrams, and some people think very diagrammatically, and they're going to help you out if you want to figure out the magnitude and direction. But there are other ways to get the magnitude and direction mathematically. So let's talk about vector A and B, and let's break them down a little bit. Let's say we know how long the resultant is, and we know the angle that they're at. Well, thinking about component vectors like that, you could break a vector into its parts. This vector has 4, so it's 4 in the x direction, 1 in the y direction. Horizontal and vertical are going to be used here. And you can use trig to figure out those components if you know the size of the magnitude and the angle. In this case, we're using theta. You can use SOHCAHTOA. Vy is going to be the angle or the velocity in the y direction. This can be broken down into a y direction velocity and an x direction velocity. Vy will be the direction in the y direction. Vx will be the horizontal or direction in the x direction. So we can break this down into Vx and Vy. If we want to look at Vx, we're going to look at the x component. Because this is the adjacent side, we can use cosine, because cosine is adjacent over hypotenuse. Because of that, we have cosine of 60, the angle, equals the adjacent Vx over 5 meters per second. If we multiply the 5 on both sides, 5 meters per second, it's 5 meters per second times cosine of 60 equals Vx, or Vx equals 2.5 meters per second. The y component is sine, because sine is the opposite over the hypotenuse. So it's Vy. This is the same as this over here, over the 5. Multiply that out. Multiply 5 on both sides. So we get 5 meters per second times sine of 60 is Vy. Vy is 4.33 meters per second. To simplify that, if you have an angle, and this is the angle, I think phi is the letter, and you know the length of the resultant, usually this side, we can multiply the resultant times sine of the angle, and this side, we can just multiply the resultant times cosine of the angle. So if we think about this guy here, and we actually do the math, we have A, which we know the resultant magnitude of 8 meters per second, and we know the angle, 40 north of east. If we're considering this like a compass rose, the cardinal directions, north of east, where east is like the x-axis. And then this is going to be 4.5 at 45 degrees south of east. We could also say 45 degrees counterclockwise, or we could say negative 45 degrees here as well. So if you break this down and want to figure out what this side is and this side is, A of x is going to be 8 meters per second times cosine of 40. So pink here is going to be cosine, because it's adjacent, times 8. A of y is going to be 8 times the sine of 40, because it's the opposite. If we look at vector b, we see this guy is 4.5 times cosine of 45 here. This guy is going to be negative. Take note. It has to be negative because it is below the x-axis here. So we have to have a negative sign here to figure it out. It's below the x-axis. So if we wanted to add these together, 8 times cosine of 40 times cosine of 40 plus 4.5 times cosine of 45 equals 9.3. We just added them together mathematically. 8 times sine of 40 plus negative 4.5 sine of 45 equals 2 meters per second. Don't forget that negative because it was below the x-axis or east. However, we can also, if we know the components, figure out the resultant. We have 2 meters per second. We have 9.3 here. All we have to do, that's triangle. Pythagorean theorem, my friend. 2 squared plus 9.3 squared. Take the square root of both sides, and r is 9.5. Sometimes we're going to use theta. Most of the time we're going to use theta, but sometimes we can use beta or other Greek letters to represent our angles. If we want to figure out the angle beta, though, we're going to use the tangent functions, because tangent is opposite over adjacent, or 2 divided by 9.3. So beta, if we want to figure out this angle, is going to be inverse tangent of 2 over 9.3, or 12 degrees. Make sure your computer's in, or your calculator's in degrees. Degrees are going to be your friend. So the final answer, you can say, what is the resultant of vector A and vector B? We can say 9.5 meters per second at 12 degrees. You could say north of east, or you can say counterclockwise, and that way all physicists would know exactly what you're talking about. They know how long it is, the magnitude, and they know the direction it's at, 12 degrees north of east, or, like I like to say it, counterclockwise. Well, that's all we're going to do today. I hope that was helpful.